Hello, Chemistry 12. This is Mr. Chan. And today what I wanted to do was add on a few things to the pH notes that you had last day. Now, today we're going to focus on one part, which is mixing two solutions of different pH values. So if you take a look, it says, so far we have focused on mixing an acid or base with water and calculating the pH. But if we were to mix two acids or bases together, we would need to calculate to see whether or not the pH of the solutions complement or cancel out in the final solution. Now, what do I mean by this? So let's say, for example, it says a 75 ml strong acid solution with pH of 3.0 is mixed with 225 ml strong base solution of pH of 8. What is the pH of the final solution? Now, for the strong acid, I am just going to circle it, okay, in red, just to color code it, okay? And I'm going to call this solution A. Okay, and the base here, the 225 mils of solution with a pH of 8.0, I'm going to call this solution B. I'm just color coding it. Now, the first step is you want to calculate the moles of H plus in solution A. Why is it H plus? Is because we are dealing with an acid. So if you have a pH is 3.00, then the concentration of H3O plus would be 10 to the negative 3. And so the number of moles of H plus would be 10 to the negative 3 molarity times 0.075 liters. And that would give you 7.5 times 10 to the negative 5 moles of H plus. Okay. Now, we do the exact same thing for solution B. But in this case, for solution B, what we want to do is we want to calculate the moles of OH minus 1. In solution B. Now, in this case, the common mistake is people see the information. You say, oh, Mr. Chan, there's a pH of 8.0. And then they just take the inverse log and they say, the concentration of OH minus 1 is 10 to the negative 8. But in this case, since it is a base, we have to calculate the moles of OH minus 1. So we have to convert the pH into pOH. So pH of 8.0, we have to convert that to pOH, which is 6.00. And what you have is when we convert that, the concentration of OH minus 1 is equal to 10 to the negative 6. Okay, so again, in this case, when we count the number of moles of OH minus 1, that would be equal to 10 to the negative 6 molarity times 0.225 liters. And 0.225 times 6. So I get 2.25 times 10 to the negative 7 moles of OH minus 1. Okay, so far so good. Now, in this particular case, notice that we have an acid solution, so we concentrate on moles of H plus, and we have a base solution mixing. That's why we have OH minus 1. So for step 3, we can say because it is an acid and base mixing, the ions, oopsie, H plus and OH minus 1 cancel. Okay. Now, if there were two acids or if there were two bases, then what would happen is the ions would complement each other. But in this case, because I have an acid and I have a base mixing, what happens is I need to cancel out the H plus and OH minus 1. So in this case, I would go moles of H plus minus the moles of OH minus 1. So in this case, what I would get is 7.5 times 10 to the negative 5 moles minus 2.25 times 10 to the negative 7 moles of OH minus 1. And what I would get in this case, minus 2.25 e to negative 7, I get 7.48 times 10 to the negative 5 moles of H plus in excess. Okay. All right, I'm just double checking my numbers here. Okay. Now, what I do here is I take this and divide by 0.300 liters divided by 0.3, and that would give me 2.49 times 10 to the negative 4 molarity of H plus left over. And then I would find the pH would be 3.603. Okay. Now, in this particular case, what happens is we have a pH of 3.60 is the result of when the two solutions are mixed together. Now, in this particular case, I gave you the solution with a pH, one with a pH of 3, the other with a pH of 8. Now, in some questions, you might be given the concentration of H3O plus and OH minus 1. Please remember that pH is just another way of describing the concentration of a acid or base solution. Okay? Now, dilutions. for a pH scale or a pOH scale on dilution, the solution would become closer to neutral. Why? When you add water to an acid-base solution, the concentration of H3O plus or OH minus 1 decreases. And as a result, the pH or pOH will start to increase. Eventually, the concentration of the H3O plus or OH minus 1 from the solution will equal that of water. Now, what do I mean by this? So in this case, if we had a 0.1 molarity HCl, the pH in this case would be equal to 1. Here, this would be a pH equal to 4. This is more dilute. So the more dilute a solution is, the closer to pH is to 7. The reason being is this. What happens is the ions from the particular substance get so spread out that it has no effect whatsoever. Now, what I'm going to do is I'm going to just show you what I mean by this. Okay? So let's say we have, I don't know, let's go, oh, there's vomit here. Let's do orange juice. Okay? Now, if I take a look at orange juice, pH of 3.5. So what that is there's a lot of H3O plus ions in the solution. When I add water, notice the pH is slowly going up. The reason being is the concentration of the ions is starting to spread out. Now, if I were to drain this and I were to add more water, you will notice the pH starts to get closer and closer and closer to 7. Now, eventually, you will end up with a neutral solution. Now, it's not to say that you don't have any orange juice particles there, but what it is that it's so spread out that it plays a very little part in the H3O plus concentration. And eventually, what happens is that there's so little in the dilute solution that it's basically the water particles that the pH meter is reading. Now, we do this in everyday life. So what happens with air pollution or even with COVID? What happens is with COVID, we say, open the windows, open everything, get good ventilation. And what that does is that it dilutes the virus particles so much that it minimizes the chances for us to get COVID. So at this point in time, that's the same idea. What you're doing is you're dispersing the ions so much, they're still present, but because they are so spread out, they have little to no effect on the overall concentration. So this is why if you ever spill an acid or base on your skin, they always say to rinse it off with water, because what you want to do is get most of it off, but also whatever's left on your skin is so spread out, it minimizes the effects. Okay. All right. Let me go back here. All right. The last thing I want to talk about when we talk about acid bases is talking about titrations. So what is a titration? Now, a titration is a drop-by-drop addition of a known acid to an unknown base or vice versa. Okay? The data that's collected is then used in stoichiometry to determine the concentration of the unknown solution. Now, in grade 11, when you did stoichiometry, all right, let me see if I have the questions here. Oh, yeah. You would have here, it's like you know, question number 13, 14, 15. What volume of 0.556 HCl has enough hydrochloric acid to combine exactly with 25.4 mils of yada, yada, yada? Now, how did they get this 25.4 mils? If you look at question numbers 14 and 15, how do they get those values? Is by the process of titration. All right. Now, a couple of key things when you're aware of titrations. When the mole of acid, or H plus donated, is equal to moles of base, H plus accepted, or OH minus 1 produced, then the titration is said to have reached stoichiometric or equivalence point. Okay? That is the definition of equivalence point, when the moles of acid equals moles of base. At equivalence points, strong acid-base titrations have a pH equal to 7. Why? Is because the moles of acid is equal to moles of base, and so what you get is you get neutral. And neutral is a pH of 7. Now, the last thing that messes people up is this. Unlike weak acids or bases dissociating in water to form equilibrium, all acid-base titrations go to completion, no matter what type of acid or base you use. In other words, the H plus ions from one reactant will always react with the OH ions from the other. Okay? There's no such thing as equilibrium. It always goes to completion. Now, let me give you an example question here. It says 10 mils of an unknown NaOH solution was titrated with 25 mils of H2CO3. What's the concentration of the NaOH solution? Well, first of all, you write the equation. H2CO3 plus NaOH gives you H2O. Well, let me just change this. Na2CO3 and H2O. Now, this is Chem 11. Double replacement reactions. You learned that last year. Okay? Now, notice all of the H plus reacted with all of the OH minus 1. And that's where you have water. Okay? We balance the equation. In this case, we have 2 here, and we have 2 here. Now, what do? You set it up like last year. So you have, what is it, 25 mils here. You have 0.30 molarity. You have 10.0 mils here. And remember, how do you solve these questions using stoichiometry? You find the number of moles, in this case, 0.3 times. So this would be 7.5 times 10 to the negative 3 moles. Remember, in this case, we need to multiply it by 2 to get 1.5. Let me just move this down here. Times 10 to the negative 2 moles. And then you divide by the volume. And you get an answer of 1.50 molarity. Okay. All this is is basically the stoichiometry calculations that you did, just like question number 15. Okay, 13, 14, 15. All right. The only thing I did was I just added a fancy term called titration. And the other thing is I just threw in a little bit of a curveball by saying it's a weak acid, strong base. But in reality, there's no difference in terms of the calculations than what you had before. Now, when we talk about titrations, how would it look? So this would be a titration, typical titration. So what you would do is, in this case, you would add a certain amount of your acid solution using something called a pipette. A pipette is basically a fancy graduated cylinder. Then what you do is you add a certain amount of indicator. We'll talk about that. And then what you do is you add, in this case, you would add your base. So in this case, here is your base. Now, so what you would do is you would take an initial reading, and then you add until you see a change in color. Then you take a final reading. Okay? And so the difference between your initial reading and your final reading tells you how much base you added. And once you get all of that information, you plug it into your stoichiometry questions, and you calculate the concentration. Now, what I have is I have two videos here that you can take a look at. Okay, so you have YouTube, question mark. This is a lowercase l that will show you a titration. And here, this other one right here shows you just in a little bit more detail of what is going on in the titration. All right, ladies and gentlemen, that is it for today. Thank you very much. Have a good day. Bye-bye.